So in this pencast I want to discuss when an operator is positive, and actually I'm also going to talk about when an operator is self-adjoint. So I'm going to work in this particular C-star algebra, E of H, right? So that's one of our most important examples. And then I'm taking an element in there, a bounded linear operator, and then the two claims I want to prove is that T is self-adjoint if and only if for all vectors in H, the inner product of T A xi with itself is real, and T is positive if and only if for all xi in H, T xi, xi is non-negative. So, of course, the beauty of these two statements is that the self-adjointness and the positivity is translated into self-adjointness, which is reality, or positivity, which is positivity of the inner product of T xi with xi for all xi. So, in order to prove this, there are four implications, and they have very different levels of difficulty. So let me start with something easy. So if I assume that T is self-adjoint, then let's see what happens when you conjugate the inner product of T xi with T xi. Well, conjugating an inner product is just changing sides, and we might as well think of this as the inner product between T xi and T star xi, because T xi, by assumption, T star is the same as T. And then, of course, this becomes T xi xi. So I'll write hence T xi xi is a real number because, as we can see, it conjugates to itself. And we can do something very similar with positivity. So we will say T xi xi. We can write this as the square of the square root xi xi. We know, let me point this out, so the square root of T is the unique operator bigger than or equal to 0, squaring to T. So I know that square root of T is actually also positive, but as you'll see in a second, it doesn't really matter. So I'm just plugging this in, and then I will put the first instance of the square root of T to the other side. I don't have to write a star because it's positive, so it's self-adjoint. And then we recognize this as the norm of the square root of T applied to xi squared. And this, of course, is bigger than or equal to 0. So this is also pretty easy. Now, to go the other way, in 1, that is actually a little bit tricky, and I'm going to give you two proofs. And so this is proof 1. And the reason why I'm giving you two proofs is that the first one is the sort of quick and dirty one, and the other one is a little bit more systematic, and I think it's worth knowing both, because the more general and slower method that I'm going to show you in the next proof is something that we're going to have to do again, or at least something a lot like it. So this is sort of a trick proof. I will take two vectors this time, psi and eta. They both lie in H, my Hilbert space, and alpha is just some complex number. And then I'm going to look at the inner product of t applied to xi plus alpha eta, comma, xi plus alpha eta. So my assumption, of course, is the right-hand side of 1. So the assumption is that the inner product of t xi with xi is always a real number. So if I do this legend here, that means that, let's say, yellow. This means that the number that I'm talking about, that I happen to know that it's real. Right? So I can do this in yellow because by the axiom, or at the right-hand side of 1, I know this is a real number. But now let's write this out, right? So this becomes, there'll be 4 terms, t xi xi, and then I have alpha t eta xi, and then I have alpha bar t xi eta, and finally alpha absolute value square t eta eta. Right, so I'm just taking these 4 terms that I get by the sesquilinearity of the inner product, and this will give me these 4 terms. And when I pull out the alpha, I will have to pull out the alpha with the conjugate from the right hand side, and that's why I get alpha conjugate in the 3rd term. But of course, this time I know these 2 terms are real, because by assumption t xi xi and t eta eta is always a real number, and I've multiplied on either nothing or the modulus of alpha squared, and that's also a real number. So we conclude that if we write alpha t eta xi plus alpha bar t xi eta, this is a real number, right? Because this is a difference between the real numbers that I highlighted in yellow, and I could write this in a slightly different way. I could write it as alpha t eta xi plus alpha eta t xi, and then the whole thing complex conjugate. So this is also real. And now, so what you can fairly easily see, I'll just write this an observation, which says that if you know for all alpha in C, you know that alpha beta plus alpha gamma complex conjugate is real, then this implies that actually beta must be gamma. So if you have a situation, and of course I want to apply this situation to my situation here where this is my beta, this is my gamma. So I'm claiming, and the observation is just an observation about complex numbers, is that if I have 2 complex numbers, beta and gamma, and they always satisfy this containment relation that alpha beta plus alpha gamma complex conjugate is always real, then actually beta must have to be the same as gamma, which is of course a trivial way that this can be satisfied. And the way you see this is that you just go in and let alpha equals 1. Then you get, of course, that beta plus gamma conjugate is R, and that's is in R. So this means that there's no imaginary part. So that means that the imaginary part of beta must be the same as the imaginary part of gamma, because after I'd make the complex conjugate, I would get minus the imaginary part of gamma, and the sum of those 2 will be 0. I can also let alpha equals I, then I get that I beta minus I gamma conjugate is real, right? So this must mean this time that when I look at the difference between beta and gamma conjugate, then I get something which is imaginary, so there's no real part, and this will imply that the real part of beta must be the same as the real part of gamma. So put together, beta and gamma must be the same. So for us, the observation gives that T eta psi is the same as eta T psi, and this is for all psi eta in H, so T must be T star. So that concludes my proof, but I'll give you another proof, right? So here's another proof, proof 2. I wrote it last time, yes. So this is the somewhat more systematic proof. So this is an argument that is called polarization. So this is something which is true for inner product, and it is good to know. So it's this formula here, k equals 0 to 3, I to k, norm of psi plus I to the k eta square, or if you like, sum k equals 0 to 3, I to the k, and then the inner product of psi plus I to the k eta, psi plus I to the k eta. And the polarization identity you simply get by looking at the sum, and then you just write it out, and then you'll see that you'll get 4 instances of the inner product between psi and eta, and then you'll get a lot of cross terms that will just cancel out. So this is something that you easily get. And the point here, of course, is that I mean, there's really nothing nice about this expression on the right hand side, except that it only involves the norm, or which is the same, it only involves the inner product of a vector with itself. And this is somehow, so what the right hand side is something that really only involves a norm or the inner product of a vector with itself. And what's useful with this equation then is that gives you a way of describing the general inner product between two different vectors, right? So these two vectors are different by sort of looking at a sum of 4 norms or self inner products put together with these powers of I. So this is something that you may already know from Hilbert space, but the point for me here is that I can use it to sort of take care of the situation that I'm in, because the situation that I'm in is that I know something about. Well, we'll come to that, but I mean, this will be very helpful for me. So so in fact, polarization holds for any sesquilinear form let's call it S from H cross H to C. So a sesquilinear form is just we've talked about this before, but this is a generalization of the inner product. It's something that is defined on 2 copies of H and satisfies the linearity properties that you get from the inner product. So it's linear in the first variable, and it's conjugate linear in the second variable. And so for the very same reason, you just write it out, and you have the same properties, so the same terms will cancel out. You get that this is true. So that's k from 0 to 3, I to the k, and then s of xi plus I to the k eta xi plus I to the k eta. So, what is this good for me? So I will consider h of xi comma eta defined as the inner product between t minus t star applied to psi, comma, eta. And it's super easy to see that this is a sesquilinear form, right? Because t minus t psi is some operator which is linear, and then you get all the linearity and the conjugate linearity properties just from the standard inner product. And then the point here is that it's easy to see that if we apply s to the same vector twice, then of course this is the inner product of t minus t psi this time. I can write this out, right? This is t psi minus t star psi, and this I can write as t psi minus psi t psi. And if you like, we can write this as t psi minus t psi, where you would generally have to put a complex conjugation, right? But my assumption, the assumption of the right-hand side of claim number 1, is that t psi is always a real number, right? So the complex conjugation doesn't really have to be there, so this is 0. Right? So what this tells me is that when I'm looking at the inner product of psi with itself here, I always get 0 out. But that tells me that if for this particular choice of a sesquilinear form, if I look at it at the same vector twice, I get 0. But that will then tell me that I get 0 everywhere because of the polarization identity I'm circling up here, right? So we get that these terms here, they're all 0, and then I have a sum of 4 zeros, so that will be 0 as well. So consequently, the inner product between t psi eta is 0, because that's s for all psi and eta. So t minus t star psi is always 0 because it's orthogonal to any vector. So t is t star, and this is what we wanted to prove. And so the tricky part of this argument is that it's very easy to see from my assumptions that t and t star will, if I put this in an inner product with psi and psi, I get 0 out. That just follows from the assumption. But to pass from this to any psi and eta, I need this polarization trick. Okay, so this was perhaps overkill a little bit, but now I've proved more than once that the right-hand side of 1 implies the right-hand side of 2. So now the only thing left is to prove that the right-hand side of 2 implies the right-hand side of 2. And this is a somewhat more involved argument than the other things that we've done that were essentially just computations. So I want to make an observation which is interesting in its own right, so I will change color here. So we can call it a lemma. So if t lies in B of h, and for some, let's say alpha strictly bigger than 0, we know that whenever we have a psi in H, then the inner product of t psi is in norm bigger than or equal to the norm of psi. So this actually has a name, so I'll write this in red. So this is called bounded away from 0. So if you look at this this statement is sort of the opposite of being bounded, right? So usually we care about the norm of t psi being less than some constant times the norm of psi. That's enough to say that t is it's continuous. But this time I'm assuming it's continuous, and then I'm asking that it somehow doesn't get too close to 0. Right? So this is somehow the kind of a dual condition to being bounded. So if that's the case, then we get 3 things. 1, t is injective. 2, th is closed. So by th I mean the image under t of h. And then 3, t star h is dense. So, and I will just write here maybe lemma plus. So if t is maybe I should call it something. I'll call this star. So if t satisfies star, and t is self-adjoint, then t is invertible. Right, and this is very easy to see, right? Because let me just point this out before I do the proof of the lemma. And so we get from here that t is injective. And we get from here that the image of t is closed. And we get from here that the image of t is dense, right? Because t is t star, so that is the same. So now we know that the range of t is dense and it's also closed. So it has to be everything. Right? So this way we see that t is surjective and injective, and then it's invertible. Right? So this is a neat way of checking invertibility of a concrete self-adjoint operator. But I haven't proved. So I need to prove the lemma, and it's relatively straightforward. But let's do it. So what is 1? So this is pretty easy, right? Because if I want to prove that t is injective, so I want to prove that if tx is 0, I should use psi. I want to prove that if t psi is 0, then psi is 0. But this is the same as saying that the norm of t psi is 0, and then by the star condition, then the norm of psi will have to be 0, and that of course can only happen if psi is 0. So that's easy. How about number 2? I want to convince you that th is closed. This is actually a lot like the argument that we used for the Gelfand transform, that the image of an isometry will have to be closed. It's pretty much the same. So assume that t psi n goes to, let's say, eta in h. Then we note that if we look at the difference between psi n and psi m, this is less than, this is the star condition, t of psi n minus psi m, with the alpha out in front. Oh, sorry, I did that wrong, right? So it has to be alpha. It's alpha inverse, right? So the reciprocal of alpha I need to write here, because the alpha goes on the right, on the right hand side, on the left hand side, sorry, in this inequality. But the point is, of course, that this thing here will go to 0. So in the sense that given epsilon, there's a big N, so that T psi n minus T psi m is less than epsilon, just because I know that T psi n is a convergent sequence. Right? But then this will also be the case on the right-hand side, right? Because of the alpha is just a constant. So the sequence psi n in n is Cauchy. So psi n converges to some vector, and I guess the appropriate letter is a zeta in H, but then T psi n goes to T zeta, but it also goes to eta, so they will have to be the same. And then we've proved that eta lies in the image of T as we want, in the range of T as we want it to. So that takes care of that, right? So maybe I'll write it carefully. So eta lies in TH, because TH is T psi, psi in H. So that takes care of that. And then finally number 3. So recall that the image of T psi's orthogonal complement is precisely the kernel of T, and the kernel of T by number 1 is 0. So this implies T star H is dense. Right, so this, I don't know how familiar you are with this quality here, but it's very easy to check. So this is a general thing, right? If you have the range of T star, orthogonal complement is precisely the kernel of T, and vice versa. And so this is a standard thing, and it follows just from the definition. So I'll just do it. Eta lies in the orthogonal complement of T star H. That's the same as saying that for all psi in H, the inner product between eta and T star psi is 0. Right? That's what it means to be in the orthogonal complement of the range of T star H, or the range of T star. That's of course the same as saying that I can move the T over to the other side. And that's the same as saying that T eta is 0, because the only vector which is orthogonal to all vectors is 0. Right, so that is what I wanted here. Okay, so all of this put together. Now I'm finished with the blue sort of sub-proof. And this is just checking that if you have an operator which is bounded away from 0, then it has these 3 properties, and if furthermore it's self-adjoint, then it will actually be invertible. And I'm going to use this in a very sort of, so now I'm back to proof of the implication from right to left in 2. And I'm going to use the purple version of the lemma. Right? So I will suppose the right-hand side, so for all psi in eta, the inner product of T psi and psi is a non-negative real number. And by 1, T is self-adjoint, right? Because to check if an operator is self-adjoint, we get that we just need to see that the inner product of T psi with psi is always real, and this is what we assume. We assume that it's even a non-negative real number. So consequently, the spectrum of T is contained in R. Right, so we need to prove that the spectrum of T is contained in what we called R plus, right? So that's just the interval 0 to infinity. And that's enough, right? Because we know that the operator is self-adjoint, so it's normal. So if we want to know if a normal element is positive, we just need to look at the spectrum and see if that is also positive. Then I will simply fix a number which is a real number and not in R plus. And then I will simply convince you that this lambda cannot lie in the spectrum. And this is again just a simple-minded computation. So we will look at t minus lambda 1 applied to xi for some vector xi. Let's square it, right? So this is the inner product of t minus xi 1 of xi by itself. So as usual, we get 4 terms, right? So I have t xi against t xi. I have there will be a minus here, so I will have minus lambda t xi xi, and I will have minus lambda xi t xi, and I will have plus lambda square xi xi. Right. So what happened here is I just computed out the 4 terms. I know lambda is real, so I don't have to keep track of any complex conjugates, and so this is correct. And now I'll do this legend thing again. I'll choose another color because this time it means that the element is in R plus. Right. So the point that I'm trying to make here is that this thing here lies in R plus. That is given by my my assumption that the right hand side of this is just because this is just the inner product of a vector by itself, and of course this is always non-negative, right? So that's easy. And so the point is that this thing here is also a non-negative number, and this is the assumption on the right-hand side of t. But look at lambda. Lambda is a negative number. So when I multiply this thing by lambda, I get a negative number. Then when I put the minus on, I actually get a positive, non-negative number. Right? And for the same reason, this is also a positive thing. So really all that happens is that I can throw away these 3 terms. They are all bigger than or equal to 0. And then I get lambda square norm of psi square. So t minus lambda 1 is bounded away from 0, i.e. satisfies the thing that we called star. Oops, blank. So t minus lambda 1 is invertible, and hence lambda does not lie in the spectrum of t. And lambda was just any negative number, and so we've proven that there can be no negative numbers in the spectrum of t, and this is precisely what we need in order to conclude that the element is positive. And so that finishes the proof of these characterizations.